is there other questions that you have from the homework or anything that you want to look at? Number 11?
Yeah.
So you got to tell me what one that is.
Oh,
6.1.
6.2.
6.211. So what was the, do you have it written down there?
No.
I have a picture of it.
So, yeah, I can pull it up also. 6.211.
In 6.5 or 6.25.
6.2.
Yeah. Oh, I think we just went over that. That's the
Yeah,
one we just
6.25
went
was the integral of cosecant
Yeah.
squared, right? Let's see.
You started,
And you said 6.211, right?
Yep.
6.211.
Yeah.
Does that look right?
Yeah. I was just having trouble setting them equal to each other to find the
intersection.
yeah.
So let's put it.
7.
I'm going to put it at the end of this section here. So I'll put any examples kind of maybe just down at the end here. And we said it was 6.2, number 11. Actually, maybe it'd be better to, no, let's put it here. Or it can't get erased. All right, so that thing, and it was just finding the points of intersection?
Yep.
So when we set them equal to each other, we're going to have, let's see if I can write on the board today. So we've got that. We've got that denominator of x, so we've got to multiply through by x in order to clear the fractions. So to clear all the fractions, I'll multiply through by 4x, get rid of all the fractions all at once. So then we're going to have 17x minus 4x equals 4x squared. That's a nonlinear equation. Nonlinear equation, everything to one side and factor.
It's just 4, right? Not 4x.
That is, oh, thank you. Yeah. That is, no.
That one's correct.
That one's
Second
correct.
one.
It's the second one, yes.
Minus 4, right?
Just minus 4. Yeah, if we multiply everything by 4x, the x's cancel in that second one, yeah. That would have been too easy if the x's could combine there. Okay, so then we end up with 4x squared minus 17x plus 4 is equal to 0. So we've got that. That looks very unlikely to factor, so we just have to use quadratic formula. So x is going to be, what is
Negative b plus or minus.
okay, so you remember that one. Negative b plus or minus the square root of b squared minus 4ac,
Over 2a.
Over 2a, yeah.
all divided by 2a.
For some reason, I was under the impression.
So we have that thing. And then we just have to simplify that, and that's going to be one of our endpoints.
Right. Yeah, thank
know.
you. That makes a lot more sense.
Yeah, it does not look pretty.
I was under the impression that you couldn't multiply by x there. I'm like, how?
Yeah, so you can always multiply both sides by something. You can always multiply by a variable. You can't divide by something that could be equal to 0.
Okay.
Multiplying is okay, though. So we don't want to divide both sides by x. It's better to subtract and factor than divide by an x, or a quantity that could be 0. Yeah, so that's just going to be a messy endpoint. And of course, it's helpful to graph it too, just to get a sense of, toss it into Desmos and just see what those intersection points look like. Any other things from the homework you want to look
I
at?
don't know if it makes a huge difference, but it's negative. Never mind, I guess it's negative.
Say that again?
I did it backwards. I flipped
Okay.
around.
Oh yeah, depending on which direction you put
Yeah.
your A, B, and C.
Yeah, sorry.
Yeah. Okay, so let's see. So we mentioned it, let's just mention again, because this is going to come up a lot. And the homework just had this one question come up a little bit early, so you've got that hint in MyMathLab that you need a power reduction identity. So these two, I just want to highlight them. We're going to look at them in a little more detail in the next section. But those are, we're going to refer to them as the power reduction identities. And they come from the double angle identities for cosine. If you were to multiply both sides by 2, subtract 1, make the signs so that you isolate, you would get cosine of 2x equals one or the other. There's two different cosine of 2x formulas that you can look at. But those two we're going to see a lot throughout the whole semester. So those two you want to focus on. So they come from this right there. That's where they come from. All right, so let's go to where we were. We were in chapter 6. And I think we were down here. We had done some disks. We had done this washer problem was our last problem. So let's come to this page and look at another example of a washer problem. So with this problem, we've got 3 curves here. We've got the square root function, we've got the vertical line over here at 4, and we've got the x-axis. So we've got that shape there. And we're going to rotate this shape around the y-axis, so it's going to create this funnel-looking solid object. And we want to find the volume of that solid object. And if we look at a representative washer, we can take this representative rectangle, it's a very thin rectangle, imagine it rotating around the y-axis, and it's going to create this washer, this red washer down there. And we're imagining, you know, all these washers stacked on top of each other. And if we can find the area of the representative washer, we integrate area to get volume. All right? Integrate height to get area, integrate area to get volume. That's going to be our progression. So if we can find the area of that washer, we integrate it, we'll get the volume. Okay, so let's take a look at this washer here. So the inner radius is this one. Let me do that in red, I guess. So there's the inner radius is the distance from here over to here. So the inner radius is the distance from your axis of rotation over to the first curve, the closest curve. And then the outer radius is the distance from the axis of rotation all the way over to the further curve. So that's going to be over here. That's going to be our outer radius. And then the area of the washer, we take that outer disk area, subtract off the inner disk area, and then we'll get the area of the washer. Okay, so the generic formula is that the area of a washer is pi times the outer radius squared minus pi times the inner radius squared. And we usually just factor out that pi, so we have r outer squared minus r inner squared. So that'll be the area of a representative washer. Big area minus a little area. So this will be pi multiplied by. Now, are we measuring horizontal distances or vertical distances?
Horizontal.
Horizontal. So any function that we have to deal with needs to be presented as an x value. Right? Functions are coins. You can either present them as x values or y values. Depends on what you need. If you're measuring horizontal, you present it as an x value. You say x equals something. If you want it as a y value, you present it as y equals something. So when we look at either curve on the ends here, they both have to be presented as x values. Well, the one on the right is already presented as an x value, right? This is x equals 4. That is this curve right here. That is the right curve. The right curve is x equals 4. Presented as an x value, no biggie. The left curve is right here. There is the left curve. It's presented as a y value. So we want to switch that, present it as an x value. So we solve for x. So that's going to be x equals y squared. All right, same curve, it's just presented as an x value. So now it's measuring distance from the vertical axis instead of measuring distance from the horizontal axis. Now we can say, okay, r outer squared, r outer is this distance from here to here. We can see, oh yeah, that's just 4, right? Doesn't matter where you draw your representative rectangle, that is always going to be 4. So we will have 4 squared. And then the inner distance, the inner radius is from there to there. Horizontal distance is always the right x minus the left x. So this red distance there, what's that going to be?
Y to the 4th.
So it's going to be that y squared minus 0. The left curve here is 0. So it's going to be y squared minus 0, and then all squared. So this will be y squared minus 0 quantity squared. That'll be the inner radius squared. And another thing in your mind is that that rectangle is horizontal, so its thickness, or it is going to be dy. And that's the thickness, which tells you you're integrating with respect to y, which also backs up the idea that everything over here should be in terms of y. Can't have any x's there. If you're integrating with respect to y, all the letters have to be y's. So that tells us that our volume will be the integral of pi multiplied by 16 minus y to the 4th dy. Integrate area to get volume. And then let's look at our limits of integration. We're integrating with respect to y, so we're looking on the y-axis for that interval. Y starts here at 0 and it ends at 2. So those will be the limits of integration, 0 to 2. Integrating a polynomial, well, let's just pause for a second. Is there any question on the setup? The rest is just mechanics of
Now, if
integration.
it didn't show you 0 and 2, would you have to set them equal to each other and find them?
Exactly. If we didn't have the graph right there, we would set, this. We have to figure out where they all intersect. So we'd have to set these two equal to figure out that point. We'd set those two equal to figure out that point. Right. Yep.
And you know it's always going to be y0 because it says y equals 0 is one of our limits
Right.
of the shape.
Yeah, so the bottom curve is going to be y equals 0. That's going to be the bottom edge of our shape. The right edge is going to be the function x equals 4, and then that will be our top. So we always have to be given enough equations to create a bounded region. We've got to have a trapped region, a bounded region. So the integration here hopefully is not too crazy. We integrate the way we do polynomials. We add 1 to the exponent, divide by the new exponent.
Doesn't 16 need y?
16?
So y.
16y, right?
16y. Oh gosh, my integration is terrible today. I'm recovering from a head cold, so I'm not 100% clear. Stay on me. Yeah, my kids went off to college, and of course, he comes home last week for 2 days when he's sick. I'm like, really? Stay at school when you're sick. Don't come home. But I like mom's food better. So then we plug in the 2, and we're going to get 32 minus 32 fifths. And
Minus 0.
subtract off 0. When we plug in 0 for the y, we'll get nothing. So we have this. And the way I'll do this, I'll factor out the 32. That common factor of 32 is pretty easy to factor out. And then we have 1 minus a fifth. And 1 minus a fifth is 4 fifths. A little bit easier than getting a common denominator of 5. And then we just have to multiply that out. So we have 128 pi divided by 5. All right, any step there you want to ask about? The nice thing so far is that with discs and washers, we decide whether we're measuring horizontally or vertically, and it's one or the other. The next technique, when we get to these cylinders, they call it the shell method, both directions come into play. Because the area of a cylinder includes both the height and the radius. So you're going to have stuff measuring vertically and horizontally. So the washers and the discs are nice because it's either this way or this way, one or the other. So, not to scare you, but but that's at least a thing that in your mind that it's either X or Y, one or the other. You don't have anything going both directions. So here's another region. So we've got 1 minus root x, that's our curve down here, that's the lower boundary. The upper boundary is y equals 1, the right-hand boundary is x equals 1. And this says, let's rotate around the line y equals 1. Not an axis. Not an axis. We're going to rotate around y equals 1. We're going to change it up because it's gotten so easy. Right there. So we're going to rotate around that axis. So that shape is rotating vertically around that line right there, and it's going to create this parabolic solid. Everybody okay with what the image looks like? And we're going to take a representative rectangle that's vertical. And if we want, we can think of that as the vertical element, integration element at x. That's going to rotate around and create that red disk over there. So if we can find the area of that red disk, we can integrate the area of the red disk to get the volume. Integrate area to get volume. Okay, well, each of these cross sections are disks. The area of a disk is pi r squared. That seems straightforward enough. We just need the area of our disk. Area of a disk is pi times the radius squared. Now, the radius here is vertical. So we want the curves that bound it to be presented as y values. Vertical distance is always a change in y. So we want the upper curve presented as a y, the lower curve presented as a y. Oh, they already are. Good. So there's the upper curve, there's the lower curve. Both are presented as y values. Vertical distance, upper y minus lower y. All right? That's how we always find a vertical distance, upper minus lower. Horizontal, right minus left. So this tells us then that the area of our disk is going to be, let's see, the upper y value is 1. The lower y value is this quantity. So it's going to be the upper y minus quantity the lower y. All that, there's the radius, upper minus lower, and then we square it. So upper minus lower, quantity squared. So this is not a washer. The squares are not on the inside. Right, with the washer, we had squares on the inside of the parentheses. Not here. So we're finding this entire vertical distance and then squaring it. So let's go ahead and simplify. This simplifies pretty nicely. We're going to get 1 minus 1, which is 0. And then the minus distributes over here to make a positive root x, but then we're squaring it. So we're going to have root x quantity squared, so we'll end up with pi times x. So that tells us the area of the disk at x. Let's just check our extremities and make sure that this is making sense. So if we look right here, when x is 0, that disk at x equals 0 should have how much area?
0.
None, right? So if we plug in x over here of 0, yeah, okay, we get 0. So that matches. If we look at the right-hand extremity over here, the radius of the disk is 1, so we should end up with pi times 1 squared, which is pi. And sure enough, if we plug in a 1 there, we get pi. All right, so that matches. That makes us feel confident that that is in fact the area function. And then we integrate the area function in order to get our volume. and we're going to go 0 to 1. And is that 0 to 1 coming from the x-axis, or is it coming from the y-axis?
X.
Coming from the x-axis. So these are, and I'm just going to draw this in here just to emphasize that these are coming from the x-axis. Because we're integrating with respect to x, those have to be x values as limits of integration. And now we have a pretty simple integral. Shockingly simple. So we'll get pi x squared over 2 from 0 to 1, which is pi divided by 2. Plugging in 0 doesn't contribute, so we just have to deal with the 1.
When we were kind of checking our work up there, how do you know if you plug in 1, you have to have pi? How'd you?
Yes. So if we look at the rightmost side here, so if we look at x equals 1, the radius of the disk here is 1. All right, so this disk over here, this far right extremity, that disk has a radius right there of 1. And the area of a disk, the area of any disk is pi r squared. So if the radius is 1, we'd have pi 1 squared, which is pi. And that's what we get when we plug in x equals 1 here.
Okay.
So that area formula is generating the proper disk areas, at least at the 2 endpoints.
Okay.
The chances of it creating the right areas at the endpoints, but not in the middle, very rare. So we didn't make a mistake.
Unless you like made up an equation, because you could just do like 1 minus x would get you technically the same correct areas at the end. But
Yeah, you could do
as long as
something.
you're trying to get it from the start,
Right.
then you're probably not going to
You
mess up.
probably have it messed up. Yeah. The chances of making, a bunch of mistakes and having the right areas, unlikely. Make sense to everybody? You see that? So super visual, this whole chapter is very visual. And we want to get really comfortable with these ideas of measuring vertically and measuring horizontally. And our basic progression. Integral of height gives area, integral of area gives volume. So it's kind of like the distance, velocity, acceleration sequence. Very similar to that. Okay, so once again, let's spin around a non-coordinate axis. So here we have 3 curves. First curve is x equals 0, that's the y-axis. Second curve is y equals the square root of x, that's our arc right there. Third curve, y equals 2, that's the top boundary. So we have 3 curves that trap that region, they bound that region. There's our bounded region. And we want to rotate around x equals 4. Okay, so we're going to spin that around. And there's the 2-dimensional shape. It's going to spin around. All I did here was draw a representative washer. Representative washer. So if we take that red segment there, spin it around, that's the washer that it's creating. Same strategy, find the area of that washer, integrate that washer area to get the volume. Same strategy. So let's look here. So from our axis of rotation, if we look at the green here, to the furthest curve, that's considered the outer radius. So the green one is the outer radius. So from the axis of rotation to the furthest curve, the furthest boundary, and from the axis of rotation to the first curve, that's the inner radius. So there's inner radius in red, outer in green. So the area of the washer, is pi multiplied by the outer radius squared minus the inner radius squared. We are measuring horizontal distances. Horizontal is always a change in x values. So that means the curves involved need to be presented as x values. Well, the curve on the left is already presented as an x value. The curve on the left is the y-axis, which is x equals 0 as an equation, presented as an x value. The curve on the right, that's that square root function, that's not presented as an x value, it's presented as a y value, so we're going to change it. We're going to make that x equals y squared. So we take that curve on the right, we change the presentation of the equation so that it measures horizontally. Now we're good to go. So our area will be pi. Outer radius, okay, horizontal distance, that's going to be this x value minus this x value, so that's going to be 4 minus 0, which is 4. And then we square it. And then the inner radius, right x value is 4. The left x value for this red segment here, 4 minus y squared. And then we square that. And that will give us our washer area. Any questions on any of those quantities? Or with the y, we do it the way we did it? So the green segment is just the distance between two vertical lines, right? X equals 0 and x equals 4. So it doesn't matter where you take your representative element, right? You could put your representative element right there if you wanted. It's still 4 units from the left to the right. And on the inside here, the inner here is still 4 minus that quantity squared. Okay, so it doesn't matter where you draw your representative rectangle. The formulas are all going to be the same. The equations are all going to pan out in the same way. So let's go ahead and simplify this a little bit. So this will be pi multiplied by, we will have 16 minus, we've got to FOIL this out. Let's be careful. So 16 minus 8y squared plus y to the 4th. 2 parentheses. And then we distribute and combine like terms. So we're going to end up with pi times 16's cancel. And we'll have 8y squared minus y to the 4th. So that measures the area of the washer at y. So let's look at our extremities. If we look at y equals 0, that washer is degenerate. It's just a circle. Doesn't have any area to it. So if we plug in y equals 0, we better get 0, and we do. Similarly, the washer at the top is really a degenerate washer. It's really a disk. Right? It's really a disk of radius 2, and the area of a disk of radius 2 is pi 2 squared, 4 pi. So let's check. If we plug in a 2 here, do we get 4 pi? Plug in 2 there, we get 32 minus 16. Did we get the right answer? If we plug in a 2 there, oh no, 4 times 8 is 32. 4 times 8 is 32. 32 minus...
And that's equal to 4 squared.
Oh, I'm sorry. I was thinking in my mind that the radius of our disk was 2. The radius of our disk is 4. 4, yeah. So we get the right answer. Yeah. So if we're coming across the top there, that distance right there is 4. So that disk up there at the top is a pi 4 squared. So it's 16 pi for its area. Everyone agree with that? So that distance across the top right there is 4 from here all the way over to here. So that disk is pi 4 squared, so 16 pi. But down here, we're plugging in a y of 2. When we plug in a y of 2, we get 32 minus 16, which is 16 pi. So it does match. It does match. All right, we ready for donuts? Who brought the donuts? Taurus. So we have colloquial expressions for all of these shapes. Mathematically, that's called a torus. Just like a washer, mathematically, it's called an annulus. It's not called a washer really, but you know, we just use the words washer and other things kind of casually. So finding the volume of this donut, finding the volume of a torus. What we're going to do is look at the generating shape and then create our math from that generating shape. So the generating region is this circle that I've drawn here in two-dimensional space. It's that bluish turquoisey circle there, disk. And if that rotates around the y-axis, we get a torus. And we want to build the volume. So we're going to build the volume using washers. So they tell us that this circle, the generating circle, is a circle of radius 2. So there it is right there. There's our circle of radius 2. This disk will rotate around and create the torus. All right. Now, if we are creating washers, we're imagining stacked washers, right? These horizontal washers are all stacked on top of each other that are going to create this torus. So we can take this representative element here. This representative element kind of matches up there. That's right there. And when it rotates around, it's going to create a red washer. So once again, we're dealing with horizontal distances. So here is the inner radius, and here is the outer radius. So the outer radius is going to come all the way across to there. That will be the outer radius. And the inner radius is here to here. So inner radius from axis over to first curve, outer radius from axis over to furthest curve. So we have our I and our RO. Those are horizontal. That means any curve that we are using as a boundary curve needs to be presented as an x value. If we're measuring horizontal, all of the boundary curves need to be presented as x values. Okay, well, let's take a look at this generating circle here. So this generating circle right there, it's got radius 2 and it's centered at 3, 0. So the center is 3, 0. So let's come up with the, come on, really? Don't do it, please. And the radius is 2.
Wouldn't the inner radius keep going till like 3? That picture?
So the inner radius is the distance from the axis over to the first boundary curve. So when we look at our shape here, this orange is the first boundary curve and the purple is the second boundary curve. So the inner radius goes from the axis over to that first boundary curve, and the outer radius goes from the axis all the way to the second boundary curve, to the furthest one. Because this shape is going to rotate around this axis, with this as the left boundary, this as the right boundary. The closer one is going to be the inner radius, and the further one is going to be the outer radius.
We're splitting the circle into 2 equations so that you're not having to deal with like a negative half of an area or whatever.
And so that's what we're going to get at right now. So the orange has to be written as an x value. The purple has to be written as an x value. How do we get those x values? We come up with the equation for the circle. The equation for the circle is going to be x minus 3 quantity squared minus y minus 0, plus y minus 0 squared equals the radius squared. So x minus h squared plus y minus k squared. So this circle is centered over here at 3, 0, so we have to shift the x squared plus y squared equals 4 circle, shift it to the right 3 units. So that's the full circle, but we need to break it apart into x values. We are told that we're measuring horizontally, so we want to create 2 different x values, one for the left side of the circle and one for the right side of the circle. So we have to isolate x up there. So to isolate x, we are going to end up with x minus 3 quantity squared equals 4 minus y squared. And then we take the square root of both sides, which is going to give us 2 equations. Well, we whenever we take a square root, there's going to be two possibilities. And then we add 3. So this gives us both equations all at once. Well, the 3 is in the middle. And if you add the square root, that moves you to the purple curve. And if you're at 3 in the middle and you subtract the square root, that moves you to the left curve. So the orange curve is going to be 3 minus, and the purple curve is going to be 3 plus. So that's how we take a circle and divide it into a left side and a right side. And you've already done this in probably pre-calc, where you took a circle and divided it into a top and a bottom. That's where you would isolate y. Like if you have a simple circle like x squared plus y squared equals 1, you can do the top as y equals 1 minus, you can do it, right? Square root of 1 minus x squared. Okay, so if we looked at a circle like this, centered at the origin, x squared plus y squared equals 1, the top half is y equals the square root of 1 minus x squared, and the bottom half is y equals minus the square root of 1 minus x squared. So we have that separates it, more intuitively, because we're used to thinking of functions as functions of x. I mean, when someone says the word function, 99% of the time you're thinking, oh, it passes the vertical line test. Right? But we're dealing with functions of y here. We're going sideways instead. So to make these functions of y, we need to break apart the circle into a left and a right. Okay, so now that we've got our curves and we've identified the inner and outer radius, we can go ahead and create our generic formula for the area of a washer. The area of a washer is always pi multiplied by the outer radius squared minus the inner radius squared. All right, it's not going to be pretty. So outer radius, again, outer radius is distance horizontally to the further curve. So there's the outer radius. That's measuring this green distance. Outer radius squared. So 3 plus the square root of 4 minus y squared, quantity squared. That's the outer radius squared, minus the inner radius, which is the left side of the circle. That's going to be 3 minus the square root, quantity squared. So that is the area of our washer at a height of y. We need to simplify that. So, foiling each of these, 3 squared is 9. And then we do left times right and double it. So it's going to be 6 times the square root of 4 minus y squared. And then we square the right side there, square that, and we get 4 minus y squared. Okay, there's our outer squared expanded. Now we have to do our inner squared. Let's be safe. Let's put this minus down here and just do this by itself first, just to make sure we're careful. So we're going to have first squared, and then first times second doubled. So it's going to be 3 times that square root, but then we double it, so we get minus 6. And then 4 minus y squared on the inside. And then we square the last there, square that whole thing, and that makes that positive. And then whatever's inside the root. And that will be in parentheses, and then close it off. And then we just have to simplify that. And we're going to get some cancellation, right? 9 minus 9, those will cancel. And then the 4 right there, minus 4, that will cancel. And then the minus y squared, this is going to end up being a plus y squared, so those guys are going to go away too. And the only part that does not cancel is the part that we really wished would cancel, the square root stuff. But that didn't cancel, so we end up with 12 times pi multiplied by the root of 4 minus y squared. So we get that. So there is the area of the washer at a height of y. Any questions on any of that? The algebra okay? Like I said last week, Calc 2, any algebra shenanigans are going to come to the surface and any trig shenanigans are going to come to the surface. You cannot ignore your algebra holes or your trig holes anymore because we are going to use it all. All right, so that is our washer formula. If we wanted to check the two extremities, our integration window is vertical here. So if we look down at y equals -2 or y equals +2, we should end up with washers of area 0. Because those points will rotate around and create circles, not washers. And sure enough, if we plug in 2 or -2, we get 0. So we probably did the algebra right. So now we have to integrate that. So we know the volume, we can factor, of course, the 12 pi can come right out in front. And we're integrating from -2 to 2. Or if we wanted, we could use some symmetry if we wanted. We have the same number of stacked washers below the horizontal axis as we do above. So we could go 0 to 2 and double it. Right? The top semicircle rotated around is the same as the lower semicircle rotated around. Let's do that. Let's use symmetry. Symmetry is always a good thing to use. So let me put a 2 out here, and I'll put the 12 pi inside for the time being just to emphasize that we are using symmetry here. So we're going to go from 0 to 2, and this is a doubling, this is a symmetry double. So that's by symmetry. All right, so then we are going to factor out the 12 pi for sure. That makes perfect sense. So we're going to end up with 24 pi integral 0 to 2. Derivatives are simple. Derivatives are like adding. You can just always do it without too much thinking if you know the rules. If you know the chain rule and the product rule and the quotient rule, I can take 10 functions and jam them all together, and most of you could work your way through finding the derivative. The hard part about integration is more complicated. It's kind of like subtraction. Subtracting is always a little more complicated than adding. Division is always a little more complicated than multiplying. Integration is always a little more complicated than differentiating. Part of the problem is that I can give you a simple looking function that you can't integrate. That's not integrable, that I can't integrate. So if you have something like e to the x dx, oh, that's simple. The integral of e to the x is itself plus a constant. All I have to do is put a square right there, and then it's not integrable. The integral of e to the x squared is not integrable by any normal techniques of integration that you'll see as an undergraduate math student. There's some fancy grad school techniques that allow you to do it, but we're not going to look at those things.
Well, what would it be though?
I'm not telling you.
What's the answer?
I'm not telling you. So it's not an easy thing to do. It's not like a simple function. But that this is one of the things that adds a lot of complexity to integration. Not only do you need to know the rules, the reverse chain rule, U substitution, your trig integrals. Not only that, you also have to sort of recognize when something is not integrable. And so at this stage, that's not an easy thing. That's something you're developing, which can only be developed by pounding your head against an integral for lots of time. And so the only technique you have, in this class we're going to learn a ton of techniques, none of them will work for that, but the only technique you have right now is U substitution. And if you were to try to do U substitution here, what you've seen so far is that with u sub, you're going to let u be the exponent or the angle or what's inside of a square root. Like that's what you let u be. So if you were to let u equal x squared here, what is the derivative? What is the derivative of this equation here? U equals, we're going to have du, oh my gosh, that. We're going to have du is equal to 2x dx. And there is no x down here to absorb that derivative. So this, if we happen to have x e to the x squared, that you can do, because the derivative of the exponent is present. If the derivative of the exponent is present, then u substitution is going to work. So the only technique you have so far is u sub, and that's not going to work there. Well, we're in a similar boat here. If we have the square root of 4 minus y squared, the only thing that you could think to do is to let u be what's in the root. Well, the derivative of that is minus 2y. There is no derivative present outside the square root. There is no y out here. If there was a y out there, bingo, we could use u sub. We can't use u sub here. But we know geometrically what that integral represents. And we can use a geometric approach. Many times we use the integral to find the volume or the area of a shape that we can't do geometrically. Like all of these curves we've looked at that are wiggly, right? We can't find a geometric way to find the area beneath a curve where the curve is not, a semicircle or something. Right? We use calculus to find that area. Well, we can go with the reverse direction too. So let's check. Let's see, what does that represent?
The volume of your shape?
It actually represents an area of something. So let's take a look. So, okay, this is a curve, right? That's a curve in the xy plane. What curve is it? So this curve is x equals the square root of 4 minus y squared. Oh, let's put it in standard form. If we square both sides and add, this curve comes from this equation here. We know that this is a circle of radius 2 centered at the origin. So there is our circle of 2 centered at the origin, circle of radius 2 centered at the origin. Okay. Everyone with me so far? So that's, this is part of that curve. Right? This is a subset of that curve. What subset is it? Let's see. Okay, well, x equals the positive square root we just did earlier with the torus. Up here, right, the positive square root is the right side, the negative square root is the left side. So this positive square root is going to be the right side of this circle. Right? That's the right side. If it was x equals negative square root 4 minus y squared, that'd be the left side. So it's the right side. Now let's look at our limits of integration. What are our limits of integration?
0 to 2.
0 to 2 on the y-axis. So the limits of integration are going from here to here. So we are now saying, if we turn our head sideways, we are finding the area between the curve and the y-axis on that interval. So from 0 to 2, we want the area between the curve and the y-axis. So this integral represents this area right here. That is the area beneath this curve on that interval. So that integral represents 1/4 of the area of the circle of radius 2.
And we just multiply that for.
Yeah. And then we multiply it. So here we go. So this is going to be 24 pi. The area of a circle of radius 2 is pi r squared, so that's 4 pi. That's a full circle of radius 2. But we have to divide it by 4 because we want 1/4 of it. So circle of radius 2, area of a circle of radius 2 is pi r squared. So this is the full circle. And we're going to just take 1/4 of that. So this is equal to 4 pi. That's the area of the full circle. Divided by 4, and we get the area of 1 quadrant. And that is 24 pi squared. So there is the volume of the torus. So a little geometry there. Questions? So let's,
So wouldn't that mean though, then that entire integral from 0 to 2 is equal to 1? Theoretically?
say that again, which integral, the,
Well, we said
Oh,
it's equal to pi.
it's equal to pi.
Pi, I mean, pi.
Yes, yes, 100%. Yep, it's equal to pi. Because the full circle is 4 pi, quarter of the circle is pi. Yep, that integral is equal to pi. Question?
Why is it 4 pi over 4?
So the shaded blue region here is 1/4 of the area of the full circle. So the area of the full circle of radius 2 is pi times 2 squared. So this is the full circle area, but we only want the blue. So we take the full area and divide by 4.
Because the equation in the integral is half of a circle, and then we're also only taking the top half of that.
Correct.
So we're taking a quarter of the full circle.
So the curve inside the integral is the right half, but then the limits of integration say, oh, only take a portion of that right half. Exactly. Now, if it was like hundreds and hundreds of years ago, and you never went more than 2 miles from your village in your entire life, you might think of this in a slightly different way. So, back in the day when you had nothing to do but math or pray, or maybe hunt, there is another way to do this, using a clever technique involving centers of mass. And there's a theorem, which you don't need to know for the test or anything, called the theorem of Pappus. And the theorem of Pappus says, hey, if we want this whole volume, what about taking the area of the generating shape and multiply it by the distance traveled by the center of mass from that generating shape? So the generating shape is circle of radius 2. The center of mass, when you have uniform density, is dead center. If you have a circle of radius 2, the center of mass is right in the middle. So what we could do is take that average point and multiply it by the distance traveled by the average point. So we could, if we were being super clever, we could say, oh, there is the average point, aka the center of mass. And how far does that average point travel?
Circumference of the circle.
Circumference of the circle of radius 3. So the circumference of the circle of radius 3 is 2 pi times 3. So 6 pi is distance traveled by center of mass. And then the area of that generating shape is pi r squared. So the area of the generating shape is pi times 2 squared, 4 pi. So that's area of generating shape. And then you multiply the two together, 4 pi times 6 pi, you get 24 pi squared.
And so that will always work for revolve shape, but you have to know the exact center of mass.
You have to know the exact center of
Usually don't.
Yeah,
Okay.
which we usually don't. So if we had some oblique triangle that was a little weird shaped, if you knew how to find the center of mass of that triangle, you could find the area of the triangle and then multiply it by the distance traveled by the center of mass. But it's a good mental exercise just to think about that. That if you take all these points in the disk are moving, right? This area of 4 pi is moving, all the points are moving, and if you take the average point and the distance traveled by the average point, it's like one of those red things that when you were a kid had the sand in it and you shook it. You know, if you're trying to find the area, say, beneath this curve, and you had one of those sand toys as a kid, okay, that area, if you shake the sand, it's going to create this. And the area of that rectangle is going to be the same as the area under that curve. It's that idea, right? If you figured out the average height of all those particles of sand, it's that same idea. The area would be the average height times the width.
So if you're ever revolving a regular shape, you can use this as a shortcut to
Yeah.
figure out.
Mm-hmm. Okay, but You'll cover some of that stuff in a physics class.
Up that second point of view, than just actually doing the regular.
Okay, why don't we take our 10-minute break now before we start shells? It'd be good to have a fresh mind before we do the integration using the shell method, since the shell method uses both horizontal and vertical simultaneously. Concept is similar. So what we have been doing is coming up with an area function that when we integrate fills the volume. And we integrate the area function to create volume. That concept still is going to persist. But we are going to create an area function now that instead of slicing our solid object like we normally have been doing, we're going to core it. So we are going to imagine nested cylinders filling out the solid. So for example, here we take this region here, rotate it around, it creates this bell with a hole in the middle. And what we're going to imagine now, instead of creating slices, what we're going to do is take a representative element and rotate it and create a little cylinder. And so what we're going to do is imagine subdividing our solid into a bunch of concentric cylinders. And if we can find the area of the representative shell, which is just a cylinder, integrate that area and get volume. So big concept is the same. Integrate area to get volume. The only difference is that our area is no longer a cross-sectional area, it is a chord area. So we're just going to take a cylinder and imagine filling out the solid. The math is very similar. The big difference is that our shape is now a cylinder. And so we have the height of the cylinder and the radius of the cylinder. The area of a cylinder is 2 pi rh. Circumference of the base, 2 pi r, multiplied by the height, gives us the cylinder. So 2 pi rh, that's what all this is representing. So this little thing here is your radius. This is your height. Oh, I said that wrong. Hold on. That's your height. Oh, no, that's right. Yeah. So 2 pi rh, 2 pi rh. X, your representative x value is just the radius to the axis of rotation. Yeah, so 2 pi rh, and then the delta x is the thickness. Because remember, we had cross-sectional area, and then when we added thickness, it turned into a rectangle. As soon as we added dimension, that's what the delta x does. It takes the cross-sectional washer and turns it into a little slab, a washer that's got thickness. That's what this does. 2 pi rh is just the cross-sectional cylinder, but then if you multiply by delta x, you get a little bit of thickness to it. So it becomes a volume instead of just an area. So again, long story short, Riemann sum, take the limit of the Riemann sum, and that gives you the definite integral. And you can see all the nested cylinders. And then we end up with this. So here they generalize the height. Maybe there are 2 curves, and so the height is the upper curve minus the lower curve. So this is just the shell height, 2 pi r is the circumference. And we'll talk about why it's an x in a minute. All right, so let's try a shell. So, very similar to the one we just sort of loosely talked about. We've got this region here. It's going to rotate around and create a bell that does not have a hole in it. And so I'm going to think of that as the representative element at x. Anytime I draw a vertical element, I'll put an x, horizontal element, a y. Okay, so when that vertical element rotates around the y-axis, it creates a cylinder. And the radius of the cylinder is right here. And the height of the cylinder is right there. Everybody see that? So that element is going to rotate around and create this. Well, I guess the front does not need to be dashed. So down here in this picture, We've got our solid object, which is a bell. We've got our red representative element rotating around, creating that red cylinder. The radius of that red cylinder is x. If we draw this vertical element at x, well, that's what x measures. X measures distance over from the y-axis. And in this case, that corresponds to the radius. All right, this x right here is measuring distance from the y-axis. So that x and that r are the same. X is the distance to the y-axis, and if we're rotating around the y-axis, then x and r are equivalent. Okay, so area of a cylinder or a shell, whatever, is going to be the circumference of the base, 2 pi r, times the height. So there's a generic cylinder, 2 pi rh. Always start with the generic. Now, when we go to substitute in for r and h, it's very helpful to know whether you want everything to turn into x's or everything to turn into y's. And if we drew a vertical element, what is the thickness of a vertical element? dx. Horizontal element, the thickness is dy. So if we have a vertical element, which is where we started, vertical element, the thickness of that is dx. That tells us everything in the integrand has to be x's. We can't have any y's in there. So that tells us that we want both of those to turn into x's. In other words, we want both of those. So there's two ways to think of it. You could think of both of them as y values, or we want everything in terms of x. And when you write y equals x squared, that's a y value, but y is in terms of x. Now when you write y equals x squared, you've written y in terms of x. If you write x equals square root of y, you've written x in terms of y. So we've got to be a little careful. The big picture is we want just x's over here. All right, so the area of our shell is 2 pi. We want x's. So now we come over to our visual, and that radius is x. So that's good. We're now doing the area in terms of x. And the height is a vertical distance. That's the vertical distance. It's already in terms of x, so we're good. So we have that multiplied by this. So that is the area of the cylinder at x. That makes sense? So then to get the volume, we just integrate that area. So v, I'm going to factor out the 2 pi. Maybe I won't factor out the 2 pi. Let's not do that yet. I'm just going to factor out the pi because I want to show you something. And then based on the image, they tell us 0 to 2. So x equals 0 to x equals 2. Okay. So we have a rational function. And the only technique you know so far is substitution. That's the only technique you know. Reverse chain rule is a shortcut for substitution. So when you're doing substitution, usually u is equal to exponent, what's in the square root, what's in the angle, or with a fraction, with what's in the denominator usually. Do you see the derivative of that denominator in that rational expression?
Yes.
Yes. So that means substitution is going to work. And this is a particularly interesting substitution that, let's do it first and then I'm going to show you. This is another really common substitution that we're going to want a shortcut for. We'll talk about why in a minute. Let's just go through the regular substitution process though. So first we're going to let u be the denominator. This tells us that du is going to be 2x dx. And we are so happy because there is 2x dx right there. So those match. That's perfect. That's how you know substitution is going to work if the derivative is present, or maybe some multiple of the derivative. Maybe you have to divide by a constant or multiply by a constant, but something close to the derivative. At least the x's have to be there. So when we rewrite this, we're going to have pi times, let's see, u is in the denominator, 1 plus x squared is u, and then the whole numerator is du. And if we go to our limits of integration, we plug in x equals 0 here. That tells us that u is 1. Plug in x equals 2 here. That tells us that u is 5. So those are the u limits of integration. And then what is the antiderivative for 1 over u? Natural log. So this is going to be pi times the natural log of the absolute value of u, from 1 to 5. And what is natural log of 1? Natural log of 1 is 0, so that lower limit is not going to contribute. It's going to contribute 0. And 5 is positive already, so we have pi natural log of 5. That is the volume. All right, any questions on that before we talk about this second important substitution shortcut? Here is the second important substitution shortcut. So you just told me this. So that we know. What is the relationship between the denominator and the numerator?
X to n minus 1.
Which is its derivative. The derivative of x is 1. When we looked over here, the derivative of that denominator was the numerator, and we just ended up with natural log, right? Pi times natural log of u. So this is going to be our general, I'm going to call this log form for an integral. So log form is if you have something like this. If you have the integral of an expression like that, consider the denominator the function, and if that denominator's derivative is the numerator, this is done. There is no more work that has to be done. This is going to be natural log absolute value of the denominator. Every single time. You don't have to do anything further. So for example, if we have the integral of x squared plus sine x in the denominator, and the numerator happens to be 2x plus cosine, you can immediately write down the antiderivative. That's in log form. The denominator has a derivative that's equal to the numerator. This is automatically, without any steps necessary, it's automatically that. Every single time. If it's in log form, which we're going to see a lot of, you can just cut to the chase. Can you work it out? Of course you can do it if you want with substitution, and there's going to be times where you probably do, but you want to get efficient at these log forms because they're going to show up a lot. Let me show you why it's true. I think you'll see it fast. So if we do this, if we have that form, if we let u equal f of x, well then du is f prime of x times dx. And that tells us then that we end up with d over u, which is natural log absolute u, which is natural log, if we back substitute, absolute f. So every single time that's going to work. If the denominator's derivative is in the numerator, you can cut to the chase. You can avoid substitution. Of course, substitution is going to work, but if you don't need it, why use it? All right, so we're going to call that log form. And Let's try another shell method. So here we've got our bounded region. Bounded region is going to rotate around the x-axis. Okay, I want to go back to the prior problem for 1 second and point something out. To create a shell, your integration element is parallel to the axis of rotation. So if our axis of rotation is vertical, to create a cylinder, we need a vertical element to create a cylinder. If our element were perpendicular, we would either create a washer if there was a gap, or a disk if there was no gap. So perpendicular to the axis of rotation creates a disk or a washer. If our axis of rotation is horizontal, perpendicular and touching creates a disk, perpendicular gap creates a washer, parallel creates a cylinder. Okay? So if we're using the shell method, we have to draw our integration element parallel to the axis of rotation. So let's look at this one. So we're using the shell method. We're rotating around x. So the axis of rotation is right here. The axis of rotation is horizontal. So if we want to create a cylinder, the element, the representative rectangle, however you want to refer to it, must be horizontal. That's how we create a cylinder, aka a shell. Perpendicular creates a washer or a disk. Parallel creates a cylinder. So this is going to be the representative element at a random y. And it's going to rotate around. There's that representative element there. It rotates around and creates this washer, which I've added thickness to it. So the height of our cylinder is that red distance. It's just that our cylinder's on its side, so the height of it's this way. And then it's going to rotate around. The radius of that cylinder is going to be this distance right here. That's the radius. And what letter is corresponding to the radius? Y. That distance right there is y. It's also the radius of this representative cylinder. So the area of a cylinder, area of a shell, is 2 pi RH, 2 pi RH. And so again, in our minds, we're imagining this horizontal rectangle. Its thickness is dy, which tells us the r and the h should be written in terms of y. We want to just have y's in there. So let's make sure that that's the case. So we have 2 pi. We look at our visual. Okay, r is being represented by y. The height of this cylinder is a horizontal distance between those two red dots. That's a horizontal distance. And horizontal distances are x values. So we want to do the right x value minus the left x value, which will give us an expression in terms of y. All right, so this x value, okay, it's not written as an x value, so we're going to change it. We're going to make that x equals 2 minus y. And then this curve right here, not written as an x value, so we need to write it as an x value, which means we need to isolate x. So now we have this horizontal distance, right x value minus left x value. The right x value is 2 minus y. Say that again. This one? If we add x and subtract y, no problem. All good. So then we're going to have 2 minus y. That is the right x value for that horizontal segment, 2 minus y. The left x value for that horizontal segment is y squared. And we're subtracting that off. So this is what makes the shells complex. We're dealing with both a horizontal distance and vertical distance. So the thing in your mind that's important is that the element, the representative element, has to be parallel to the axis of rotation. And then think to yourself, is it a dy or a dx? Because that gives you a clue as to whether you should have y's over here or x's over here. And because that horizontal element has thickness dy, we know, oh, everything has to be written in terms of y. We want only y's over here, no x's. So it's a super helpful way to keep everything straight. All right, so we have 2 pi integral. And let's FOIL this out, or whatever we call it, distribute the y. We have that. And then our limits of integration are coming from the y-axis. And what do you think those are going to be?
0 and 1.
Yep, 0 and 1. So we have these horizontal elements that are all kind of stacked up between 0 and 1 on the y-axis. So 0 and 1. And that integral is not too hard. So make sure that the setup is good, because that setup is absolutely essential. Any question on the setup or anything you want to ask about how to think about it or how to start it? Or one thing that's going to be really helpful is to get in the habit of whenever you draw a horizontal element, put it at a y, and anytime you have a vertical element, put it at an x. It wasn't vital for the discs and the washers, but for shells it really helps. Because you can see that the radius here then is the y value. It's this generic y. So I would definitely recommend doing that. So the integration, we just have a polynomial, so we use our regular polynomial integration technique. Add 1 to the exponent, divide by the new exponent. Do that 3 times. Then our volume will be 2 pi multiplied by negative 1/4, negative 1/3, plus 1. So it looks like the common denominator is a 12. So we're going to have a negative 3, a negative 4, so that's negative 7, plus 12 is 5. So that'll give us 5 pi over 6.
10 pi. Or, oh, yeah.
10 pi, and then we divide by 2, and yeah,
Yep.
we'll get to the
That's the 6. Yeah.
5 pi over 6, that's the volume. Dang, it looks like an angle. Numbers can mean anything.
And so the reason we would want to use the shell method here instead of a washer method is because for a washer you'd have to do 2 different volumes, right?
So, great question. So this region, we could subdivide it into 2 pieces. We could subdivide it right at this transition point right here. And we could use the disk method with each of those functions, for sure, and then add them together. Absolutely.
But it's just faster to do it this way.
It's going to be faster, and sometimes
And sometimes it won't be possible.
it won't be possible to
It's
use
like
another.
2
If
curves.
the function generates something that you can't integrate,
Yeah.
so there's going to be times where you can't integrate, or perhaps times where that's usually the trouble is that you couldn't integrate it. Like these, we could integrate both of those pretty easily.
But you had like some weird.
Some weird function like
Self-overlapping.
inverse sine or something, and you don't know how to integrate inverse sine. It's like that homework question. They changed the order of integration because you don't know how to integrate inverse sine, but you could, move the sine to the other side of the equation, and then you can integrate.
Okay.
So yeah, there'll be times where, and on the test I'll tell you, use disk, use washer, use shell, so you know. You're not. Okay, so here's a little region, that little triangular-ish region. The right curve, like that thing right there, that looks like a curve that would be very, very hard to write as a y value, if not impossible. to solve that for y. Okay, so we've got that curve, and we've got these x values right here, 1 over root 3 and y equals 1. And y equals 1 is that one. And we're going to rotate around the x-axis. So once again, if we rotate around the x-axis, if we are going to use a washer, we would use a vertical element because that would be perpendicular to the axis. But we want to use a shell, so we're going to use a horizontal element. And that horizontal element is at a random y. All right, so now that element is parallel to the axis, so that's going to create a cylinder. Perpendicular, it would create a washer. Parallel creates a cylinder as it rotates. So we want to use that. And now let's figure out the stuff. So this distance right here, that's going to be the radius. Distance from your element to the axis of rotation, that's the radius of the cylinder that's going to be formed. And the height of the cylinder is just this red segment's length. So call that h. So it's a sideways cylinder. The height is this direction, sideways. Now we go to our generic, the area of a cylindrical shell, 2 pi RH. 2 pi RH. And before we start filling in the blanks, let's think to ourselves, horizontal element. Thickness of the horizontal element is dy, so we are integrating with respect to y, which means the r and the h need to be replaced with y's. We want to write them in terms of y. All right, so that's good. So that gives us 2 pi. How about the radius? Y. That's what y represents. And the height, they've already done us a favor. The height is horizontal. Horizontal means right x minus left x. The right x has already been written for us. Right? We don't have to isolate or change anything. And the left x is that 1 over root 3. So this tells us that the height, so let's put little dots here to represent the left and the right. So there's the left x, there's the right x. So we're going to do the right x minus the left x. So 4 divided by y plus y cubed, right x minus left x, which I'm going to write as root 3 over 3. All right, so there is our generic cylindrical area. Now we integrate that in order to get the volume. Integrate area to get volume. So the volume integral, we're going to integrate, and we're going along the y-axis now because we have horizontal elements. They're sliding through y, along a y interval. And they're sliding from 1 to root 3. So limits of integration, 1 and root 3. And let's see, so let's distribute this y to the inside. We're going to have to subdivide this into 2 integrals at some point. Come on, let's see. So distribute the y here, we get 4y over y plus y cubed minus root 3 over 3 multiplied by y times dy. So we are going to, let's pull the 2 pi all the way to the front, and then we're going to end up having 2 separate integrals. Now, in this first integral, we see a common factor of y, and we really want to do this. And then the second integral, let's just get all the way through this and we'll talk about whether that's legit or not legit. So can we cancel out that y? So the problem with canceling something out is that you might lose, you lose a solution if you're solving an equation. And what you would have to check, it's perfectly fine to divide out something that's not 0. Now, you can cancel any common factor that's not 0. You can certainly cancel out a common factor that's not 0. If you look at our interval of integration, is y ever 0 on this interval? And the answer is no. If we look at our picture, we're up here, y equals 0 is down here. Y is never 0 in this integration, so we can, in fact, just cancel it out. You can always cancel a non-zero factor. So we'll cancel that out. And now this first integral is going to be an integral that we are going to see all too much of this semester. And maybe you haven't done it yet, but if you look at the handouts, you should have done it in Calc 1. If we go to the integration stuff here for these 3 right here. So we're going to do a lot with those 3 functions that integrate to the arc functions. So the one we're looking at right now is this one. So that's the one we're going to see, of all those 3, we're going to see all of them a lot. Well, maybe I shouldn't say a lot. The arcsecant we are not going to see a lot. We are going to see the arctan a lot. We're going to see the arcsine from time to time. But arctangent we are going to see a lot. So that's going to be the most important one to get down. But we will use the other 2 also. So arctangent is super common. And the reason is that it shows up a lot. It's a really interesting function. So let me just remind you of what arctangent looks like. For most students, it's the first function that you encounter that has 2 horizontal asymptotes. There is a horizontal asymptote at pi over 2 and a horizontal asymptote at negative pi over 2. So the inverse tangent function is bounded between negative pi over 2 and pi over 2. Okay. So that integrand right here, we can imagine factoring the 4 out, and then we're going to have 1 over 1 plus y squared, which is arctangent of y. So again, that's going to be the most common of these functions that integrate to an arc function. And then over here, we have regular polynomial business, so we're going to get the square root of 3 divided by 6, y squared from 1 to root 3.
The y above, when you, I guess, canceled the y, you just canceled it, you didn't actually factor it out?
Well, if we factor the y out of the top and factor the y out of the bottom, then they cancel.
Oh, okay.
Right, so you can think of distribution in lots of ways. Like if we have, all those markers seem bad on the board. Like if we have some sort of expression like this, you can multiply through by x. If you do the same thing to every term, you've essentially multiplied by x over x, right? If you just multiply everything through by x. The same goes with cancellation. Like if we have something like 10 over 8 plus x, let's make that a 4x squared. You could divide everything by 2. If you do the same thing to all terms, essentially what you did was this, where you divided this 2 into that, and you divided that 2 into these. You can do it that way. Conceptually, it's just simple to think about doing the same thing to all parts of the fraction will be, the way to think about it. So you could also think of it this way: divide the top by 2 and take the bottom and divide by 2. Like there's lots of ways to think about it. The end goal is that if you do the same thing to all the parts of the fraction, you're good. And so in this one, we're saying, oh, divide this by y, divide this by y, and divide that by y. which is essentially factoring out the y from top and bottom and then having them cancel.
And it's also fine because y will never be 0, so dividing by 0 doesn't matter.
So the only reason we can do it is because y is never 0 here. Yes.
If y was 0, we'd lose at 0. Because
If y was 0,
the
we'd
top
be,
is undefined at 0, and the bottom, this simplified equation is not undefined at 0.
correct.
So we're losing information between the two of them, technically.
And in this case, we're actually not losing information because y is never 0.
We don't
which
care
is-
about 0.
We don't care about 0 in this case. So, that puts us in this scenario. And the evaluation then, we can distribute this 2 pi in a minute. Let's just leave it here for now. Just try to go inside and keep it simple as possible. Let's use a bracket just to. So we're going to have 4 times arc tangent of root 3 minus arc tangent of root 1, of just 1. I guess root 1 is 1. Arc tangent of 1. And then over here, we put in root 3 here. Root 3 times root 3 is 3. 3 over 6 is a half, so we're going to end up with minus root 3 over 2. And then we subtract off what happens at the lower. So we have minus a minus, which is plus. And plugging in 1 there gives root 3 over 6. So we end up with that. All right, any questions on that substitution? Fundamental theorem stuff. Okay, back to trig then. So, we need to remember how to evaluate inverse trig functions. We're going to do it a lot. Inverse tangent, all the inverse trig functions are restricted angles. And the inverse tangent function is going to be restricted to the right side of the unit circle. So inverse tangent is always on the right side of the unit circle. And you don't include these endpoints. It goes between minus pi over 2 and pi over 2. Inverse cosine is always an angle on top. Inverse cosine goes 0 to pi. Inverse sine and inverse tangent are always on the right, negative pi over 2 to pi over 2. If you think in your mind, you can go to a unit circle, and basically the angle interval that you want is the angle interval that gives you all possible values. Like if you think about inverse cosine is on the top half of the circle because it's going to give you all the cosine values from positive 1 over to negative 1. Right? Cosine can go from negative 1 to positive 1. And so if you take the top half of the circle, those values are going from negative 1 to positive 1. Inverse sine is on the right-hand side of the unit circle because sine values also go from negative 1 to 1. And sine is the y-coordinate on the unit circle, and so those y values from negative 1 to 1 happen on the right side of the circle. And the same is true for inverse tangent. Inverse tangent values go from minus infinity to infinity, and those happen on the right-hand side of the circle. We'll talk more about it as we continue on, but for now, we just want to be clear that inverse trig functions are angles, and they are restricted either to the top half or the right half of a unit circle. So inverse tan is always restricted to the right half, which means minus pi over 2 to pi over 2. Okay, so let's look at inverse tangent of 1 first, because that's simpler. So in your mind, you should be saying angle on the right with a tangent value of 1.
Pi over 4.
Pi over 4. When you are looking at the unit circle and you are looking at tangent values, tangent is the same as slope. So we're thinking about the slope of the terminal ray. So when you look at this picture right here, and we say, okay, we want the angle on the right with a tangent of 1, we are saying we want the angle on the right where the terminal ray has a slope of 1. Right? Tangent is y over x. That's slope. That angle right there is pi over 4. So this in here is going to be a pi over 4. So that one is the easier one. And let's get a common denominator over here of 6. Multiply this one by 3 and 3. So we're going to have negative 3 root 3 over 6 plus root 3 over 6. So that's going to give us negative 2 root 3 over 6. So that's that side. And then we have to fill in that one. Okay. So in our head, we are saying to ourselves, what angle on the right has a tangent value of root 3? In other words, which angle on the right has a terminal ray with slope root 3? I heard both candidates. One was right, one was wrong.
Pi over 3. Do a pi over 3.
So at pi over 6, what is the slope there at pi over 6?
1 over root 3?
1 over root 3. Or you could write it as root 3 over 3. And this one up here, that one has a slope of root 3. So the slope here is root 3. And the slope of this one is 1 over root. I'm going to write it as root 3 over 3. It's a third as steep. Okay, so if you do, the point on the unit circle for this one is root 3 over 2 comma 1/2. Do y over x, you get that slope. The point here is 1/2 comma root 3 over 2. Do y over x and you get that. So root 3 is the steeper one. Root 3 over 3 is the shallower one. So that is going to be a pi over 3. So we're going to have 4 times pi divided by 3. All right, and now 4 also needs, I guess I didn't distribute it to here. Let's distribute the 4 simultaneously. So we have that. So the 4 goes to each of those angles. Now we just need to simplify that, and then we'll be good. Let's see. So we end up with 2 pi multiplied by, so that's going to be 4 pi over 3 minus pi. So 4 pi over 3 minus 3 pi over 3 is 1 pi over 3. And then simplify this, we'll get root 3 over 3. And that's probably a reasonable way to write the final answer. You could factor out that denominator. Doesn't matter. Either way is totally fine. That will be our whatever. What were we finding? Volume? Long ago? All right, any piece of that causing you consternation? Yeah.
Up towards the mid area, you did root 3 over 3 y, and then you integrated that.
This one here?
Yeah, I'm just confused why I got integrated your root 3 over 6.
So when we integrate y, we get y squared over 2.
Oh,
So the over 2 part puts a 2 in the denominator, and then all the denominators need to be multiplied together.
and you just moved it out and multiplied it back. Okay, that makes sense.
Yep. Any other piece that? Yeah, there's a lot of moving parts with these integrations. A lot of shell, a lot of things just moving, and we all think of it maybe slightly differently. So it's good to ask. Okay, so random axis, shell method around other lines. The shell method wasn't complicated enough. But our basic principles are going to stay the same. So we're going to find the area of a cylinder and integrate it. And to find the area of a cylinder, we need the radius and we need the height. That stuff all stays the same. And then it's going to boil down to, okay, are we dealing with vertical? If it's vertical, upper minus lower. If it's horizontal, right minus left. So we just keep sort of distilling ourselves down to some basic geometric principles.
Area of a stadium.
To what?
Area of a stadium.
Area of a stadium, or volume.
Oh,
Volume of a
volume,
stadium.
volume of a
Volume of a stadium. Exactly. Let's do it. All right. So there's our region. These are the bounding curves. So those three curves intersect and create that little shape, that triangular-ish shape for our Colosseum here. And the axis of rotation is vertical. And they say we want to go around this line, x equals -2. So this axis is vertical, right? So that means we want to create an integration element that's parallel so that we end up with a representative cylinder, not a disc or a washer. Okay? If we chose a horizontal element, bless you, which we could have done, then we would end up with a washer if we chose a horizontal element. We want vertical to create a cylinder. The radius of that corresponding cylinder is this distance from there to there. Right? That distance is the radius of the cylinder. We're creating this big old cylinder. That's going to be the radius. The height of the cylinder is usually obvious. It's whatever the length of our representative element is. And I'm going to put this representative element that's vertical, I'll put it at x. Okay. Generic cylinder/shell area is 2 pi RH. So 2 pi RH, generic cylinder area. All right. So let's first ask ourselves, should the R and the H be in terms of X, or should they be in terms of Y?
X.
And they should be in terms of X. We've drawn a vertical element. When we draw a vertical element, we think of its thickness as dx, which tells us the integration is with respect to x, which means the R and the H have to be written in terms of x. So what is the radius then?
X -2.
Close.
Plus 2.
X plus 2.
Oh, yeah, because minus and plus.
So it's a horizontal distance. The right x is just x. The left x is -2. So it's x minus -2, which is x plus 2. Or you could even just look at it visually and think distances. You could say to yourself, oh gosh, this distance is 2, and this distance is x. And that x is positive because it's to the right of the origin. So you could think of it that way also. So that total distance, that cumulative distance will be x plus 2. But our basic principles of right minus left still work. X minus -2. The height is vertical. So vertical, we want to do upper y minus lower y. And if we look, our upper y, okay, it's already isolated properly, right? We want it written as a y value. That's how it's written. So the upper y is y equals x squared. The lower y, which is just the x-axis, is y equals 0. So it's upper y x squared minus lower y, which is 0, so it's x squared. So there is our cylinder area as a function of x. So then the volume will be the integral from, what do you think the limits of integration are?
0 to 0. 1. -2 to 1.
First off, are we looking at x-axis or y-axis? X-axis.
0 to 1.
So ask yourself, on what x interval do the elements live? It's like, okay, no elements are over here for your region, so there shouldn't be an x value included over there. So you can imagine drawing your representative element in all of these positions that are between 0 and 1. Right? Because each one of those elements represents one of the concentric cylinders. So our interval should only include elements that are in the shape. So we only want elements that are in that shape. So we're going to go 0 to 1 from the x-axis. All right. 1. So So then we're going to have 2 pi. We'll distribute the x squared. So we're going to have x cubed plus 2x squared. And integration element dx. So that'll be the volume. So this will be 2 pi multiplied by the quantity, x to the 4 over 4, plus 2x cubed over 3 from 0 to 1. Zero does not contribute, so we can focus on the 1. We have a fourth plus 2/3, common denominator of 12. We're going to have 1/4 plus 2/3. So that'll be 2 pi multiplied by, that's going to be 3 plus 8, which is 11 over 12. So 11 pi divided by 6. That'll be the volume of our Coliseum, or the volume of the bleachers.
When you ask us these, will we always have a picture, or could you just ask us the words with nothing else?
If things are in the beginning here, I'm drawing the pictures deliberately to make sure that we can see how the geometry works. I will not always draw it for you though.
Okay.
But ones that you do have to draw on your own will include functions like that,
Yeah.
not functions like that.
Okay, gotcha.
Right, so basic exponential, basic polynomial, but none of these weird rational functions or inverse trig functions. Yeah, nothing too weird.
And if you don't give us a picture, you should recommend drawing a picture right
Definitely.
away. Okay.
Definitely.
Yeah.
So, is this just an example, or was there a reason that we couldn't do the washer method?
This is just an example. We could try to do it with the washer method.
All right.
Yeah, let's just set it up. Let's split this page a little and let's try to do it with the washer method right above it. Why not, right? So let's just move you down. And so if we attempt the washer method, let's see, sometimes it'll work, sometimes it won't. Let's see. So I think I can take that shape. Let me just grab that image, and I think I should be able to just grab that and put it down here. And then we can start over. Let's see if we can do it. Now I can't take out that vertical thing there. So if we were going to do it with a washer, we would choose a horizontal element, so ignore that other thing. And this distance here, let's use the red to represent from here to here, that's going to be the inner radius, right to there. So between those two dots, that's from the axis of rotation to the closest curve. And then the other distance we'll call the outer radius will go from axis of rotation. I didn't want an arrow to there. And that's going to stay 3 all the way right throughout. The outer radius will always be 3. Okay, so let's go ahead and set this up. So the area of our washer, pi our outer squared minus our inner squared. Our outer, like you just said, is 3, so this is going to be pi times 3 squared minus. Okay. Our inner, we need that curve presented as an x value because we're measuring horizontal distances. That distance is horizontal. Any boundary curve that we use needs to be presented as an x value. That's y equals x squared up there, so it's going to be x equals, we have to decide. Is it x equals positive square root of y or negative square root of y?
Positive.
Positive, because these y values are above the x-axis, so they're positive. So we're choosing the positive square root because that's the one that makes the most sense. Okay. So now it's going to be our inner squared. So that's square root of y, quantity squared. So this will
Y
be,
plus 2, no?
say that again?
Square root of y plus 2, because it's all the way to the negative 2 for our energy.
Oh, gosh, thank you.
Otherwise, that'd be very easy.
Yeah, that seems way too simple, right? So we're finding this entire distance right here.
Entire R.
Yeah, so for this one, is everyone clear that for that one we did do 1 minus minus 2?
Yeah.
Right, because we're at this axis of -2, and I was spacing out for a second thinking we were just at the origin, but we're not at the origin. So it's this one minus this one. So it's square root of y minus minus 2, so it's square root of y plus 2. That quantity squared.
That's why it's difficult.
There we go.
It's just 1.
Everybody okay with that? So the left x value here is that -2. Okay, so pi multiplied by 9 minus, FOIL this out and we get y minus, so the inside here, a times b doubled, so that's 2 root y doubled is 4 root y, and then distribute the minus sign. And then square the last, we get 4, distribute the minus, so we get -4. So there is the area of our washer, so pi multiplied by 9 minus 4 is 5, so 5 minus y minus 4 root y. Good. All right, so then we just integrate. How about limits of integration?
0 to 1.
0 to 1, because we're going horizontally, so we're going 0 to 1. So the volume will be the integral from 0 to 1. We can factor out the pi. And when we integrate a square root function, it's easier to convert it to a rational exponent. Then we can just use the power rule. So the power rule, so we're going to have pi. We get 5 times y minus y squared over 2 minus y to the 3 halves, adding 1. Divide by 3 halves means multiply by 2/3, which will give us 8/3. And that goes 0 to 1. So we'll end up with pi multiplied by 5 minus 1/2 minus 8/3. Common denominator of 6, so it's going to be pi times, so it's going to be 30 minus 3 minus 16. So 30 minus 19, which is a point, what is it? 11. 11 over 6, and let's hope that that was the same answer we had above. Was it?
It was.
Oh, good. Oh, good. It better be, right?
Yeah.
Better be.
Math works.
Woo! Math works. Math is reliable. So in this case, it didn't matter. All right.
Thanks.
All right, let's try one more. Or why don't you all try this one? So set this one up. At least set it up. So same shapes. This is a y equals x squared. You're going to rotate around this line up here at y equals 2. That's your axis.
And the constraints are y equals 0, x equals 1.
Correct. Yes. What'd you all get for your R?
2 minus y.
Perfect. 2 minus y. Does everyone agree and see that? So we chose a horizontal element at a random y. So the radius of the cylinder that's created, it's a vertical distance. So we do the upper y value, which is at y equals 2. So this is y equals 2 up here. And the lower y is just y. So it's going to be 2 minus y. How about the height?
Square root of what?
So this is a horizontal distance. Horizontal distances require x value subtraction.
Or square root of x?
So the x value over here is 1. The x value over here is root y. So it's going to be 1 minus root y.
There's 1 minus, oh, because it's on the other side.
So it's here. So the right x is 1. The left x is root y. And then if we FOIL this out, let me do it in descending order. So we're going to end up with positive y to the 3/2, and then minus y, and then minus 2 root y, and then plus 2. FOIL it all out. How about limits of integration?
0 to 1.
0 to 1 I agree with, from y or from x?
X.
I've heard both. So did we choose a horizontal element or a vertical element?
It's in terms of y.
So it's in terms of y.
So this is a horizontal element and its
dy.
thickness is dy. So that means we zip over to the y-axis and look at a y interval. So our integration interval is going to be these y's over here from 0 to 1. So the volume will be 2 pi integral 0 to 1 of these 4 terms. We got that. And integrating polynomial type things, add 1 to the exponent, divide by the new exponent. So here we're going to add 1 and get 5/2. Dividing by 5/2 means multiplying by 2/5. Here we add 1 and we get y to the 3/2. Dividing by 3/2 means multiplying by 2/3, so we get 4/3. And then 2y, 0 to 1. So we've got a bunch of stuff to add together here. 2/5 minus 1/2 minus 4/3 plus 2. Looks like the common denominator is 30. So that'll be 12, and then minus 15, and then that one's 10, so minus 40, and then that one is going to be 60. That one's over 1. We want to get to 30, so multiply top and bottom by 30. So that's going to give us 20 minus, that's 20, minus 2 is 5, so 17 pi, cancel out a 2 over 15. That'll be our volume. All right, questions on the dy versus the dx, on the limits of integration, on any of the integration? Anything rubbing you the wrong way with this one?
Yes, it did.
Or does it feel like good times? Feels like good times. All right, so let's take a look at our last slide. Probably won't make it through the whole thing, but we're going to find the volume of a napkin ring. So napkin ring is a sphere with part of it drilled out. So we're going to take a circle of radius 6.
That was this week's video.
Oh yeah, that's right. Yeah, if you watch the, yeah, that's an interesting video.
Yeah.
Right? Okay, so this is going to be our basic setup. Long story short, we're going to use that region right there. That gray region rotated about the y-axis is going to generate the napkin ring. Now we can also use some symmetry. And we could just focus on the top here. And that rotated around the y-axis will create the top half, and then we could double it. All right, so we're going to use the washer method. So the area of a shell method. So the area of a shell is 2 pi RH. 2 pi RH. So for us, that's going to be 2 times pi. And when we look over here, this distance is, whoops, not there. Here, this is the radius. Come on, you can do it. Wait, what? How did that happen? That is not what I drew.
You drew a squiggle and then you expanded.
Yeah, I guess so. Weird.
It's almost now, it's monthly till now.
It is almost Valentine's Day. So this is the vertical element at x. There's our radius. The height of our cylinder is that to that. So let's see if we can do that. Everyone agrees, I think, that the radius is x? This circle is a circle of radius 6. And we want this vertical piece, so we want the upper half of this circle. That's going to be y equals positive square root of 36 minus x squared. Come on. Can't rush on this board. You can't go too fast. So we solved this for y and we chose the top half. Solve that for y and choose the top half. And so that's what's going to go right there.
And if you've chosen the bottom half, you just end up having to do 0 minus.
So if we wanted to choose the bottom half, we would integrate from down here to up here, and our height would be 0 minus a minus, which we could absolutely do that.
And since it's -5 to 0 instead of 0 to 5, then you end up getting the same.
Except that's not
Oh, no,
negative
no,
5 down
that's
there.
That's not your bounds number.
Which is good. Does everyone agree that's not negative 5 down there?
Yeah, it's not.
That's like negative 5 plus epsilon. That's positive 5 plus epsilon. We're lucky we're integrating with respect to x because that's there to there. That's 3 to 6.
And this is another good reason to use
That direction. Shell instead of washers.
Because you could do this with washers, you just have to figure out what that weird
What that weird value is.
Gotcha.
Exactly.
Okay.
All right, we'll stop there. We'll take a 48-hour break. No, 48-hour minus 2 hours minus epsilon.
And that's
48 minus some change.
48 minus 250.
Yep. All right. See you on Thursday. Welcome to week 2. We have some nice weather outside. Don't be distracted. Stay focused. Become an integration ninja.
It's just going to get harder and harder to say.
Right?
Nice the weather.